we are going to be looking at modelling with linear equations. We've come across some things with modelling before already. In fact, we saw in chapter 2 that lots of things in real life have a quadratic relationship. We talked about things like vertical height with time, and actually the context for that vertical height with time, we've talked about it a couple of times, was like a ball being thrown, or maybe an arrow being fired. Anything about the way it falls under gravity has that kind of quadratic relationship. But actually, lots of real life variables have a linear relationship. And what that means is there is a fixed increase or decrease in one variable each time the other variable goes up by 1 unit. So loads and loads and loads of things in life have a linear relationship. It means that as one thing goes up a constant amount, the other thing also goes up a constant amount. So I've just got a few kind of examples of things. So car sales made and take-home pay. That's because if people work in selling cars, the amount of money that they take home is just proportional to how many cars that they sell. It's a slightly different kind of thing. You don't get paid per hour, you would get paid commission of how many cars that you sell. There's also the relationship between Celsius and Fahrenheit. We obviously use Celsius for the way that we measure temperature in the UK, but have you probably heard of Fahrenheit? Fahrenheit is like a different kind of system. Where do they use Fahrenheit? Yeah, in America. And America tends not to use anything that makes sense with like measurements and stuff. Like, yeah, they don't use anything metric. They use everything imperial, but not like European imperial. They have their own system, and it doesn't really fit with anything. So they use Fahrenheit, but there is a linear relationship between Celsius and Fahrenheit. I think the relationship is for Fahrenheit, you take the Celsius, you multiply it by 1.8, and then you add 32. So we've already kind of got a sense of the gradient is 1.8 and the intercept is 32. So when you have freezing, which it's almost like outside today, if it's 0 degrees Celsius, you times that by 1.8, you get 0, and you add on 32. So in America, when it's freezing temperature, they would say it's 32 degrees, which doesn't feel particularly useful. And they talk about things that are hot, very, very hot day being 100 degrees. So you could think about how you would find out what Celsius was, subtract 32 and divide by 1.8. So it's got a linear relationship between Celsius and Fahrenheit. I've also then got an example of something to do with geography, that temperature and altitude in a particular location. What does the word altitude actually mean? The height, yeah, the height above sea level, like how high up you go. What kind of relationship will there be with temperature and altitude? Yeah, the higher you go, the colder that you go. It may not be linear for the entire section of something, but perhaps for certain parts of altitude, there will be a linear relationship between those things. There's also linear relationships in things within maths as well. So it's not just going to be something that's useful for real life, it's also useful for maths life. So the nth term of an arithmetic series, the nth term is a linear relationship. For every time you move across one position, you're increasing by a particular amount. So we could see that actually the nth term formula is just another version of a linear relationship, because each time it's going up the same amount. So here, I've got an example of a graph on the top, and actually it's related to the temperature and altitude that we had. It seems to make sense. We always seem to put along the x-axis, we put the variable which is the independent variable, which means that it's probably easier to define actually the dependent variable, which we put as the y-axis. The temperature depends on the altitude. Yeah, so the temperature is the thing that relies on what the altitude is. So we always put the thing along the bottom that's the thing that we can't actually change. The thing we put along the side is the thing that changes according to the thing along the bottom axis. It'll make more sense when we see a few more examples with stuff like that. So it says here, the temperature y at different points on a mountain is recorded at different altitudes x. Suppose we were to use a linear model y equals mx plus c. They've done a few different plots here, and they've put in a line of best fit, which we can obviously see is going to be a linear model that we have. It says determine m and c, and it says you can assume that the line goes through 0, 70 and 250, 20. So how would I be able to find out m if I know that it's going to go through these 2 points here? Gradient, so I'm just going to do the change in y over the change in x. The change in y appears to go, so we've got 20, take away 70, which will be minus 50, and the change in x is 250, take away 0. So that's minus 50 divided by 250, which is minus a fifth. What is the value of C in this case? Pardon? Yeah, it's just 70 because they've conveniently given us this coordinate that we've got here straight away. So that must mean then that the equation of the line that we have is that y equals minus 1 over 5x plus 70. Part B is perhaps where things get a little bit different, and it's maybe asking us to do something that's slightly changed from what we've done in GCSE. It then says to interpret the meaning of M and C in this context, and I've underlined these two different things. Interpret means to say, like, what is the significance of them? What do they mean? Interpret, what's its meaning? And when it says in this context, that means you need to relate it back to what the question is talking about. So I'm just going to give you a few seconds. What do you think in this context the meaning of M means? And what do you think the meaning of 70 means in this context? So just take 30 seconds to talk to the person next to you. What are your ideas of how you might answer question B? Okay, so I'm interested to hear, Locke, what do you think that either M or C means in this context? Yeah, so that's one of the interpretations. Why did you say the lower the temperature, the further that the altitude increases? Ah, so you've looked at the graph, but what is it about the value of M that we have here that tells me that?
It's minus.
Yeah, it's minus. So we've already interpreted part of it, that the negative is saying when the altitude is increasing, the temperature is decreasing. But I actually think for A-level we need to be even more specific by interpreting the meaning of M in this particular context. Anyone think they can give a more specific definition of, or a more specific interpretation? Red one, what were you going to say?
For every meter that you go up, the temperature decreases and goes into.
Excellent. I'm going to write that down. For every meter, every 1 meter, the altitude increases, the temperature decreases by 0.2 degrees, and in this case it's Fahrenheit. Because really that's what the definition of gradient is. For every one space you move in the x direction, that's what changes in the y direction. Depending on the context, it may make more sense to say for every 10 meters the altitude increases, the temperature changes by 2 degrees. I'm not saying that's necessarily better, but if this number was very, very small, if you're trying to communicate that to, I don't know, a group of scientists or something, you might like to actually change the numbers a little bit to make them make a little bit more sense. For every 100 meters that the altitude increases, the temperature decreases by 20 degrees Fahrenheit. Maybe it gives a little bit more context for humans to understand it. As mathematicians, I am very happy with this sentence, but I'm just saying, you know, if in the future you're using maths to try and convey information, you might like to try and convey that information not using necessarily 1 meter. You might like to use it with more to try and give a greater sense of what's actually happening. So we took the hardest one first. We've looked at what the meaning of M is. What is the meaning of C then in this context? Ishraq? Yeah, at sea level, the temperature would be 70 degrees Fahrenheit. So let's write that one down. At sea level, the temperature, I'm going to say, is predicted as 70 degrees Fahrenheit. Sea level is obviously when the altitude is 0. So the last part of the question says predict at what altitude the temperature reaches 0 degrees Fahrenheit. Now Fahrenheit, is that the x-axis or the y-axis? The y-axis. So all it's really saying is when does y equal 0? So I'm going to just take that equation that I have there and I'm going to say that y is equal to 0. So I get minus a fifth x plus 70 equals 0. So a fifth x equals 70. So x equals 70 times 5, which is 350. And the units would be meters. Okay? That kind of makes sense. If you imagine this graph continuing all the way down, it looks like it probably will be crossing the x-axis at 350. Yeah. Yeah, you could also do 70 divided by 0.2 and that would give you the same thing as well. What was your thinking behind doing 70 divided by 0.2? Yeah. Yeah. Yeah, absolutely. I suppose that way is kind of like a common sense way of doing it, which is a great way of doing it too. I suppose this way of doing it is almost like a maths kind of way, and I'm not saying that either of those ways is better. It's actually nice to be able to see both of those ways at the same time, okay? So you can start seeing now why we're interested in when we've been looking at previous questions and the question says, where does it cross the x-axis? Where does it cross the y-axis? It's like, okay, well, it's probably not very interesting by itself, but to know what its significance is in context questions, maybe it's a bit more interesting. Okay, so what we're going to do is we're going to have a look at a couple of different exam questions. We're going to look at this question that we have here, and then you're going to have a go at this question that we have here, okay? Now, this does not look like, on the surface, this does not look like a graph question, okay? But it is actually going to be a graph question. Because you've got this in front of you, I'm going to just shrink it down a little bit so that I have a bit more space to do some of the working out. What we're going to do first of all is we're going to read through this question. A tank which contained water started to leak from a hole in its base. The volume of water in the tank 24 minutes after the leak was 4 meters cubed. The volume of water in the tank 60 minutes after the leak started was 2.8 meters cubed. The volume of water, V meters cubed, in the tank T minutes after the leak started can be described by a linear model between V and T. The first thing it wants us to do is to find an equation linking V with T. So there's some really important things that are coming up in this question. Arguably, the most important thing that I think you should see in the question is that it says the volume of water V, T minutes after the leak, can be described by using a linear model between V and T. Linear model is like the code language that we as mathematicians use to say, this is a straight line graph. This is something that we can model using a relationship between V and T. You will have a look at questions we've already done where there's a quadratic model. That quadratic model would be things like the Archer question or the rugby ball question. In the future, you will also look at some models that could be exponentially modelled or logarithmically modelled. So it's really important that when you see this bit, it tells you what we're going to do in the question, because there will be other types of these that you come across in the future. We need to make sure that we understand what a linear model means. So we're going to try and find this equation that links V with T. Now I'm going to just get rid of this picture of the man here, and I'm going to do a little bit of a graph sketch of what we think this might look like, okay? With our two variables that we have here, which one do we think is the independent one that should go along the bottom? If you were going to draw this as a graph, what would you put along the bottom? Yeah, you would definitely put the time along the bottom, and along the side you would put the volume. We're now going to go back to what the question is saying. We've got this tank and it's leaking with water. It tells us that 24 minutes, the volume is 4. So I would encourage you to do a sketch of what this might look like. At 24 minutes, the volume is 4. So I can put here that that would be 24, that would be 4. So its coordinate would be 24, 4. And as soon as this graph is drawn, the question just becomes so easy, okay? And also, there are many, many ways you could solve this. This is just the way that I like to do it and the way that I think is going to be the most sensible for us to stick with doing, okay? If you're like, I wouldn't do it like that, I'd do it like this. That's okay, but I'd like you to try and experience this way that we do it. It then says the volume of water in the tank, which is 60 minutes after it started, was 2.8. So now if I go all the way on to 60, along the bottom, the volume has changed to 2.8. So I have the x, or the t coordinate is 60, and the v coordinate is 2.8. You could easily do this question without the graph, but the graph is actually there to link it back to what we've been doing for the last 2 lessons. It reminds us that we can use graphs to model things. And it tells us that there's a linear model between them. What does that actually mean, that there's a linear model between them? What could I add on to the graph that might be sensible? I could add on a line, yeah, I could add on a straight line that passes through these points. I've not maybe made my graph quite long enough, but I've got it going all the way down to the bottom because eventually this tank is gonna be completely empty. Okay, now we've actually drawn something that might help us think about what's going on here. We want to find an equation linking V with T. So, I have got 2 points, this point and this point here. I might even write them out again. I have 24, 4 and 60, 2.8. What do I need to do to find an equation between these 2 lines? Ariful? Good, I'm going to find out what the gradient is. So to find the gradient, I'm going to do the change in y. So I might do the 2.8 take away 4, divided by the change in x, which is the 60, take away 24. And we're going to be moving now into decimals rather than fractions because we're doing a real life thing. So we've got minus 1.2 divided by 36. So we get m is minus 1 over 30. Actually, you know what? I think we should stick with that as a fraction because otherwise we go into recurring decimals. Now we're not going to find out what c is because that would be doing y equals mx plus c. We don't use that formula anymore. What's the formula that we use? M brackets x minus x1. Okay, so I guess we could just need to be careful here because this is to do with y and x, and our question is to do with v and t, and we have to make sure that t is where the x is. So I'm just going to rewrite that formula underneath. It will be v minus v1 equals m brackets t minus t1. And then we can dive straight in with what the equation is going to look like. We can either use this coordinate or this coordinate. I'm probably going to use this one, and I'm going to call that T1, V1. So I get V minus 4 equals minus 1 over 30, T minus 24. Technically, that is the answer to the question. Remember how I said, unless it says make V the subject or whatever, this is technically the answer. If you were in a mad rush and you were just like, I have to be finished, then that's fine. but we're going to just make it look in the more familiar form, just so that it makes a bit more sense. So I'm going to just expand the brackets, because I think it might be useful to have V as the subject here, so that we get a direct relationship of what the volume is equal to. So volume minus 4 equals minus 1 over 30 T, and then I've got minus 1 over 30 times minus 24, which is plus 4 over 5 when we calculate that. So the volume is equal to minus 1 over 30 T plus 24 over 5. If you did it in decimal form, that would also be okay. If it was in decimal form, we would have had minus 0.033 T plus 4.8. It depends on what the context of the question is. Depends how you're going to use it, okay? Let's just quickly remind ourselves what we did. We drew a graph to make the question become just about finding the equation of a line. We then knew that we had two coordinates. We found the gradient, we used the formula, and we came up with the equation. You'll be amazed how many year 12s last year and year 13s would see this question and just get it really confused. Draw a diagram, whole question becomes super simple. Okay, so we're now going to just finish off. We're going to just do part B and then part C together as well. I might see if we can even answer part B at this top part of the page. So it says, use this model to find the initial volume of water in the tank. When it's saying the initial volume of water in the tank, what do we know about V or T at that point? The initial volume, yes. Good, T is 0. Initial means that T is 0. So looking at the formula that we've got down here, we can clearly see that V would be equal to just the 24 over 5. So V is 24 over 5, which is 4.8 units. Meters cubed. The whole question has been talking about meters cubed. Careful, some questions might switch the units and you just have to make sure that you convert the units midway through the question, okay? It then says the time taken for the tank to empty. When it's talking about the tank being empty, what do we then know? The volume is 0, so we've now got that V is equal to 0. So if we come back down to this one that we've got here, we would have 0 equals minus 1 over 30 T plus 24 over 5. So we get 1 over 30 T is 24 over 5. So T is 24 over 5 multiplied by 30, which is 144 minutes. If it asks for that in hours, obviously you could convert that to hours by taking off 120 for 2 hours. And then we've got one last bit to answer, which I'm probably not going to fit up there. I'm going to have to probably squeeze it down here. It says, suggest a reason why this linear model may not be suitable. So why the linear model may not be suitable. Have you, if you've got a bath in your bathroom and you have a bath, do you notice anything about the way when you take the plug out of the bath, what happens to the water? It goes at a different pace. When does it go faster? When it's more full, it goes faster. Do you know why it goes faster when it's more full? Yeah, because there's more pressure on it. So actually something that we should probably say here is that tank of water, it's probably not going to come out at a constant rate. So for part C, why the linear model may not be suitable, because water is unlikely to leak out at a constant rate. If you want to give more detail, you can say it will leak faster at the start. So there are many ways of doing this question. You could use Redwan's idea of common sense of thinking, okay, well in 36 minutes it's changing by this amount, so this is how much it would change in 1 minute, this is what this would be. But I find students get confused with that. If you can just draw yourself a diagram and be like, oh, it's just a normal find an equation of a line question, it suddenly just becomes super simple. So on your very back page of the booklet, you have got a question which is about the height of a plant. And this is an exam question that was done by an AS paper a couple of years ago. Okay, so I'm going to give you a bit of time to have a go at that one, and then we'll do some practice.